All right. So last week we started talking about probability and how we can figure that out. We're going to start looking at combining probability with the distributions and other things that we talked about in chapters 1 through 4. Because the same concepts that we did there can be used for this stuff as well. So first, a couple little simple variables or definitions. When we're talking about a random variable, it is a numerical outcome of a random process. So when we're rolling a die, it's going to be the number that comes out, or flipping a coin, whatever it happens to be. So it has to be numerical. So if we're flipping a coin, heads and tails, that wouldn't be numerical. So we've got to somehow make it numerical. So if we're going to count the number of heads, that would be numerical. Or if we set heads to 1 and tails to 0, that would also be numerical, things like that. So they have to be numerical so we can do our calculations with it. And a probability distribution is just a model which describes that random process. So it's going to show you what the values are going to become over time in those that process. All right, so discrete random variable. So what makes something discrete?
The different data points, there's nothing in between.
Right. And continuous?
There is always something in between.
Yeah. You don't just jump from 1 to 2, you go through everything in between. So we are going to look at two different types of variables. We're going to look at the discrete ones and continuous ones. We're going to do discrete this week. Continuous is actually going to be next week because it's a little more complicated when we're looking at the distributions. So for discrete random variable, there's 3 things that we should be able to do to describe it. We should be able to state the variable. We should be able to list all the possible values of the variable. You do not necessarily have to list them all out numerically. You can list it out in words. You can explain what it is. And we should be able to somehow determine the probabilities of these variables. All right, so let's look at this example. A very simple example, the toss of a die. So the random variable is the outcome of the toss of the die. When you roll a die, it is numerical by it's 1 through 6. So that automatically is numerical, so we don't have to worry about that piece. The range of values, all integers between 1 and 6 inclusively. So you could have just done 1, 2. You could have actually written out 1, 2, 3, 4, 5, 6 if you wanted to. That's fine as well. Now the probability distribution on this one is easy because it's a die. If it's as long as it's a standard die, everyone has a 1/6 chance of coming up. So the one thing you're going to notice that's different about this is the symbols on the side. So because they're variables, we actually can start looking at them in terms of x's and things like that. So your first row is what x equals. The second row is the probability of when x equals whatever that number is. So this right here would be the probability of x equals 1. And this would be like the probability of x equals 5. How you'd write that. So I know it looks weird when x equals x, but that's the second x is the one that gets replaced by the number up on top. Simple enough? We can do things that are more realistic as well. So not everything is always going to be dies and coins and cards. So the number of defective integrated circuits received in a batch of 1,000. So the number of bad chips in a box of 1,000 of them. So our random variable is the number of defective chips. So what are the values that I could get? It's like basically anything from 0 to 1,000, right? None of them could be defective. All of them could be defective. Is this discrete or continuous? Why? Yeah. We're counting the actual number of defective chips, and if it's half defective, it's defective. So it would actually be, this is discrete values. Now, they say the probability distribution is unknown. We would have to collect some data to be able to determine this. unlike rolling a die, it's not always going to be like, okay, the chances of a box out of 1,000 of 3 of them going to be just is 1 out of 1,000. That's not necessarily true. It could be random. So we would have to collect some data to be able to analyze the actual distribution for this. The head nurse at the hospital is trying to determine the capacity requirement for the nursery. So my random variable is the number of babies being born. Range of values, well, we can have no babies born, or we can have hundreds of babies born. We don't know. So that's why it goes to some large positive numbers. Like, we don't know where it's going to end. Probably could, more data we collect, we could probably get the general idea, but it could technically be any number. The distribution, the same thing. We would have to go back and look at historical data to be able to come up with that. It's not necessarily going to be an exact specific number. Is this discrete or continuous? Discrete. Yeah, can't have a half a baby. That'd be kind of disturbing. So a local restaurant has made a policy that states lunch will be served in 15 minutes of ordering, or it'll be free. So obviously there's a lot of stuff that goes into this, but they're measuring the time. So the random variable is the amount of time between ordering the meal and receiving it. So it has a range of values from 0 to infinity. I probably wouldn't wait an infinite amount of time to get my sandwich, probably a couple hours. And even if it's free, I'm probably not waiting that long, especially for lunch. Is this continuous or discrete? This is continuous because it's time. And the same thing with the probability density, I'd probably have to go back and look at historical data to be able to determine that. But we could. There is a possibility of being able to come up with that. All right. The total number of points in a football game for a local high school team, continuous or discrete? Discrete. The daily price of a stock, continuous. The interest rate charged by banks for a 30-year mortgage. That one could be seen both ways. I would go continuous because you're going to have a decimals in there. You're not jumping directly from 5% to 6%, for example. You go through different values in there. I would say it's continuous, but this is one of those ones that our Hawks can be a little iffy sometimes on it. So they could say that's discrete. I'm not positive. The number of times the backup of a computer network is performed in a month, discrete or continuous? Discrete. The amount of sugar imported by the U.S. in a day. Well, it depends on the question. So we had this with my last class. It depends on how they're measuring it, right? If it's measuring it by weight, I would say it's continuous. Someone goes, well, what if they measure it by package? I'm like, well, then you got to figure out what kind of package. And it doesn't say that in there. So I'm going to assume they're talking about weight in this problem. And I would say it's continuous because weight's typically continuous. So, yeah, I'm going to go off on a limb and go, they're counting this probably by the amount of tons of sugar that is being brought in the United States each day and then consumed by all the coffee drinkers. All right. Discrete probability distribution. So whenever we're looking at a list of values, we can make a distribution out of it. So we looked at that before. We were talking about bar graphs and stuff like that. Those are just distributions. So we need to be able to look at in terms of our probability to be able to show that as well. So a couple of the rules that we looked at last week about probabilities are still true and actually are just as important in this respect. So the sum of all the probabilities have to equal 1. So when you add them all up, they have to equal the 1. The probability of any value has to be between 0 and 1. If it's 0, what does that mean? It can never happen. If it's 1, what does that mean? It'll always happen. And if I gave you a probability of 1 in a distribution, do I have any other values? No, because it has to equal 1, right? So if it's 1, there's no other values that would exist. Okay. The other thing is every possible value has to have an associated probability for it. Okay, so you're not going to have values that are just there that don't have any probability. You could have a 0, that's possible, but every possible value of X needs a probability that goes along with it. So if we look at a coin flip. So remember, if we're flipping a coin 3 times, remember last class we came up with those events, the tails, 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 heads, tails, those type of things. Notice how that's not my events that I'm looking at. It's the number of heads. Because again, we need to have it as a numerical value. So we've got our number of heads here. 0, 1, 2, 3. And then our probabilities are next to it. So the probability of getting 0 heads is 1 out of 8 because there's 8 events and only one of them has no heads. 1 head, there's 3. 2 heads, there's 3. And 3 heads, there's only 1 possible outcome is that as well. If you added all those probabilities together, what do you get? 8 out of 8, which is 1. So these do add up to 1. So this is a discrete random probability distribution. Okay. Again, not everything has to be in terms of a game or things. So Mr. Johnson is a computer salesman. During the last year, he kept record of his computer sales for the last 200 days. He sold no computers on 40 days, 1 computer on 20 days, 2 on 60 days, 3 on 40 days, and 4 on 40 days. How many computers did he sell? Not 10. How many days did he sell 1 computer? 20. So how many computers did he sell? 20 in those 10 days, that one day, right? He sold 20 computers, 1 at a time. Then he sold 2 computers on 60 days. That was 120. So you got to multiply them to get the total number of computers that he sold. It's going to become important in a little bit. So we did this over 200 days, right? What's the probability that he'll sell at least 2 computers each day? So to do this, we have to change this information into a probability distribution. So we have our X and our Px of X. So 0, 1, 2, 3, and 4. So how would I figure out the probability of 0? He did that in 40 days out of how many? 200. So I would do 40 divided by 200. Which is, you can give it to me as a decimal, 0.2 or 0.20. And then I would do 20 out of 200. 10. And these we already did, so I don't know how to write those. Is this a probability distribution?
Yes.
Why?
They add up to 1.
They add up to 1. Everyone has a value. Now that we've got a probability distribution, what is the probability that you will sell at least 2 computers each day? 0.7.
Oh, I did. At least 2.
At least 2. So I'm adding up the 2, the 3, and the 4.
Oh, 2. Oh, I went backwards.
Oh, okay. Yeah, we're going to do 2, 3, and 4. So at least 2 means 2, 3, or 4. So that would be 70 or 0.7. The probability that he will sell at most 2 computers each day. That's the other direction. So that's 0, 1, or 2. So in that case, that'd be 60% or 0.6. The wording matters. If he said the probability that he'll sell greater than 2 computers each day, that's just 3 and 4. Or less than 2 computers each day, that's just 0 and 1. So depending on how it's worded depends on what you need to look at. And I know the last class was talking about, I guess it was 6.3, that a lot of the wording was like, it was very specific on how it was worded. And if you didn't read it, you end up getting them wrong based on what they were asking. So be very careful on how they're wording those. All right. There's no way this is accurate, but we're going to go with it. Is this a probability distribution? Yeah, it adds up to 1, and that's what matters. An investor has decided that she'll purchase stock if there's at least 50% chance that the stock will be more than $32 in 30 days. So is she going to purchase the stock? What is the probability that it's going to be more than $32 in 30 days? 0.2, just the 0.15 and the 0.5. It's 30.5 and 33. We would not add the 32 in that situation because it says more than $32. Okay. So in this case, and actually in this situation, even if you did, you'd still get the answer right because it was still under 50%. But make sure you're reading the terms correctly. Is price discrete? No. That's why I said this is not a very good example because stock prices would be continuous, not discrete. But they did this. So, all right. So in chapters 1 through 4, when we were starting to look at data, what are some of the calculations that we were able to do to figure out the data or to figure out information about it? What are some of the terms we found? Mean, median, and mode. Okay, what's mean? Yep, add them all up and divide. Was there multiple ways that we could find mean, or was it just always just add them all up and divide by how many you had? There's a couple different ways we can do mean, right? So technically, yes, it is always add them up and divide. However, you're not always going to have all the data written out that way. So there's 2 other methods that we use to find mean. Huh? I didn't hear what you said. That's why.
I said the Q2, but then I realized.
So Q2 is what? That's my median. So median is the middle number, which is another value. And then mode's the one that appears most often. We had trimmed mean, where that one we'd also still have to have all the values, right? There was one that we were allowed to do where data was kind of grouped. You use it to figure out your grades quite often. Weighted mean. So in a weighted mean, we multiplied them by how many times that number occurred, and then we added them up, added those values up, and then divided it, right? So when we're looking at a frequency distribution, we kind of have that type of situation. We're telling you that this is the number that I have, this is the value of X, and this is how often it occurs, right? It's actually exactly the same as figuring out your grade. The percentage of your grade should add up to 100. That's just like your probability down the bottom. And these would be the pieces that are associated with it. So what this actually is called in terms of a frequency distribution is what's known as expected value. So it's going to give you what the value should happen over time. It is the exact same thing as mean, and that's why they use the same symbol for it. Remember that little M symbol or that little U, funny U symbol? That stands for mean. So it's the same situation. So if you see expected value, it is the exact same thing you were doing with a weighted mean. So let's find the expected value of this situation. So we're going to take each of these and multiply them. So 0 times 0.2, 1 times 0.1, 2 times 0.3, 3 times 0.2, and 4 times 0.2. Now add all those up, and what do you get? 2.1. Does that make sense for the mean? Yeah. 2 is the one that is the highest, right? 0.3. And 3 and 4 has a higher percentage than 1 and 2, or 0 and 1. So I would expect my mean to be pulled a little that direction. So 2.1 makes sense. That's, in this situation, this is the number of sales that he would have. So on average, he would have 2.1 sales per day. And that would be his expected value. It's called expected value more often because when you're using it in terms of gaming, we're talking about money. So expected value tells you how much you'd be expecting to win every time you rolled the die or played the game. And then you compare that to how much you're spending to determine if you're making money or you're losing money. Most games that you'd play at a casino, you're going to lose money. The expected value should always be a little less than what you're paying in. Otherwise, the casino wouldn't make any money. You can get lucky, but in time, that's what should happen. All right, let's look at these two situations. So these two are investments. So you've got option A and option B. So which investment would you rather take? Okay, why? Okay. So let's look at what are some ways that I can describe the data that might help me compare them to determine which one's a better option.
And take the weighted in the book.
Yeah, we can find the mean, so the expected value of it. Okay. Which one of those do you think has a higher expected value? Without calculating it, just looking at it. B? Okay. What are some other calculations we can do? There's another one that we use to be able to compare information and data. Started with an S. Standard deviation. What does that tell us? What was standard deviation giving me? What's the piece that goes into standard deviation? That started with a V. Variance. So variance means how much things are varied, right? How far it's spread out. So standard deviation gives me a value of spread. So the lower the number, the more consistent they are. The higher the number, the more spread out, more risky it would be. So depending on how old you are, depends on how much risk you'd want to take. So if you're younger, the higher standard deviation might not be an issue because you can accept that risk. If you're older, you might want a little lower of a risk value there. So again, just like I told you before, you are not going to have to calculate these out by yourself. There is a site I posted out of my website. It's called Statology. And it's got all these statistic calculators. And one of them is called the probability distribution calculator. It does all these calculations for us. So here you're going to type in your probability and you're going to type in the value of it. So for example, 21331. That it, and then I screwed it up 1. Oh, I think it's 1 at the end, right? Yeah, it's 1 at the end. Okay, that was negative 1,000. Anyway, scroll down, we calculate. I screwed something up. Is it negative? That was negative 2,000. I'm like, I know the answers. And that wasn't the answers. That's the answers. So it will calculate your mean or your expected value. It will also calculate out your standard deviation. It'll also give you your variance too. So you can use this to do the calculations in Hawks and on your test. I looked at Rougarou. It does not have a calculator to be able to do this, at least not that I was able to find. And this just is way easier than what we had there. So, all right. So my expected value would be $900. So I would expect in option A to earn my expected value would be $900. That'd be my profit. So I'd be making money with a standard deviation of 1757. What about option B? Would you expect a higher expected value or a lower expected value? Lower? Why lower? Okay, so we have a couple more negatives in there, right? Okay. So you have, again, it's more risky, right? But we have on the other end, we have more money too, right? The 2, 3, and the 4, that's higher than the 1, 2, and the 4. So there's a bigger chance there of making more money too. So we would also expect our standard deviation to be a little bigger too in this case because it's a bigger spread, right? So my expected value for this is $1,400. So it's definitely higher, but my standard deviation is also way higher. Okay, so yes, if we did it long enough, we'd earn a profit of $1,400. So that basically means every time you do it, you'd earn a profit of $1,400. So if this was monthly, yearly, whatever it happens to be, you earn a profit of $1,400. However, since it's a mean, that's the average of a lot of different possibilities. So 1 month, if let's say this is monthly, 1 month you might lose $3,000. The next month you might lose $3,000. But the next 3 months you might make $4,000. So it's like you don't know. It's a matter of it's vary, but over time, your average should come out to be about $1,400 a month. Does that make sense? Okay. That's that. All right. So here is the dice problem. So you're going to play a game and you're going to roll and it's going to cost you $10 to play. Okay. So 20, 0, 0. All right. Find me my expected value of this. Expected value is easy to calculate, so that's why I'm not. So we're just taking each of those values and multiplying it by the 1/6. Add them all up. What do you get? What was it?
Oh, sorry.
You forgot to subtract this other one. $10. You're multiplying by 1/6 or dividing by 6. So it depends on how you want to look at the fraction. All right, so I got $10. So I'm paying $10 to play it. My expected winnings is $10. Is this a good game to play? You're not going to make anything. The longer you play, you're basically going to break even in this situation. Is this a good game for me to have you play? Would this be a good casino game? No, why? You're right. They're not making any money either, right? If you look at this, see how that -20 in there, would that entice you to play or make you go, I really don't know if I want to play this? Okay, because you don't want to have to lose more money, right? All right, so let's make a change. We'll change that to 0. But that's going to be 1, 5, and we'll keep that at 50. Now what's the expected value of this game?
$9.3.
32 or 33, something like that. It's something like that. Would you be more willing to play this game or the first game? Before you did the calculation, just looking at the numbers. This one, because there's no -20 in there, right? But this one's worse. This one's great for me. Actually, that's about the way the casinos work. Okay. Like a 90% expected value is what they shoot for in most of their games. So that would actually be about what the casino is. So the longer you play this, eventually you're not going to have any money left. You're going to start losing money because you're going to pay $10 and you're going to lose 70 cents every time you play. Yes. Oh, this set? I just made it up.
1, 5, and 50.
Yeah. So then I'm hoping they did the calculation correctly, but let me actually do it to make sure. So you multiply the 1 times the 1/6, you should get 0.17. 5 times that should be 0.83, and that should be 8.33. And that should come out to be, yeah, I believe that's 9.3 or 9.33. Okay. So whenever you're playing a game, the expected value is what you're going to look at over time. And you'd always expect it to be on the other end. If somebody gives you a probability and it's way above what you're betting in, play it. You're probably going to make a ton of money. But you might lose some. Okay. That's what expected value is. And that's the usefulness of expected value. All right, a couple more, and then actually we're done because half of your class didn't show up. Is this a probability distribution? Huh? Why? Right, doesn't add to 1. Has to add up to 1. If it doesn't add up to 1, it doesn't work. Is this a probability distribution? If it added up to be 1.01, would that be a probability distribution? If it added up to 0.99, what happens sometimes when you like put numbers and you only do it at 2 decimal places? You have to do what? Rounds. Sometimes 0.99, 1.01 is just a rounding error. So if it comes out to be those, I wouldn't say, nope, it's not it. Normally, if it's not a rounding error, it's going to be way off, like the 4/3 situation. I actually don't know this. I'm going to suspect this one does come out to be exactly 1. But I'm saying when you're looking at numbers, if it comes off and it's slightly off, it could just be a rounding error. That does happen sometimes. All right, so they want to determine if they should get the helicopter for their hospital. So if we plug these numbers into the wonderful little calculator that I told you about,
Is that on your
it is on my website. I've linked it on the top of the post for today's notes. So yeah, I did make sure I put it there. Oh, it's not there. All right, I have to type them back in again. I need the numbers for the notes. So my mean or my expected value is 2. So on average, I would have to transport 2 critical patients each month. And then my standard deviation is 1.3 and my variance is 1.84. What's the probability that the helicopter will not be used to transport patients at all that month? 0.15. What's the probability that the helicopter will be used at least once to transport critical patients? How'd you get it?
I subtracted the 1.15 from 1, so that is
Right. Remember the complements. We just figured out nothing. The complement of nothing is at least 1. So I could just do 1 minus the 0.15 to get the 0.85 instead of going through and adding up the 0.2, the 0.34, the 0.19, 0.06, 0.05, and 0.01, which I saw quite a few people in here doing because I could sit there and look at your faces as you're going, trying to add the numbers together. Remember, complements can be very, very helpful. Yes.
How did you find how it won't be used?
Oh, it's just 0. Won't be used as be just a 0. 0 patients means they're not using the helicopter that month. So that was just that 0.15. And then the next one says at least once, that'd be 1, 2, 3, 4, 5, or 6, which would be the complement of the 0. What's the probability that the helicopter will be used at most twice to transport critical patients? .69. Because we're adding in the 0, the 1, and the 2. Okay. That's it. Wednesday's class will be a little more complicated. Not horribly, but a little more.
Did you go over the expected value equation? Just say 200.
It's just adding them up. It's just this. Hold on. It's just the sum of, where's the formula? There it is. You're multiplying the x times the probability and adding them. Yeah, that's what that little symbol right there just means sum. So when we did this one, you did 0 times 0.2, 1 times, and then you added up those values to get the 2.1. That's all it is. Yes. That one? Bye, guys. I'll see you Wednesday.
Have a good day.